we had started on three-phase AC voltage controller with R load at a firing angle of 60 degrees. So we'll look at it for a firing angle of 30 degrees, which will probably tell you how you are really having variations in the voltage waveform. So let me try to take it for alpha equal to 30 degree for R load. So I am trying to look at R load with alpha equal to 30 degrees, right? Then we will proceed to RL, and with that we will conclude AC voltage controller. We are not going to dwell on it for too long. So we said that we are going to have three-phase voltages, and I am going to have one, this is A phase, so 1 and 4, then I am going to have B phase, which we call 3 and 6, and then C phase, which is going to be 5 and 2. And then we are connecting the load here. I have taken star connected source and star connected load, and AC voltage controller is just connected in between, right? So if we are looking at this with alpha equal to 30 degrees. So these are the three-phase voltages that I need to draw. So this is one of the phase voltages. So I am going to have this as the 60 degree gap, and then let me draw the second phase, which is going along somewhat like this, right? And the third phase, which will go along somewhat like this. So this is A, this is B, and this is C, and we are firing at 30 degrees, which means we are going to fire one here, then, oh, I am sorry, one here. I am drawing it as though it is rectifier. So one has to be fired here, and two has to be fired here. So this has to be erased. Oh, the entire waveform is erased. Okay. So this is somewhat like this. So 2 is fired here, then 3 is fired here, and so on. You guys understand that this is alpha equal to 0 for AC voltage controller, right? So because of which I have 1, 2, 3 and so on like this. So when I fire 1, I assume 5 and 6 are conducting. So if 5 and 6 are conducting, 5 corresponds to C phase, but C phase negative happens only from this point, not before that. So I am going to have C phase negative only from this point. So I still have 30 degree interval before device number 5 goes off. So I am going to have, so let me draw the intervals. So this is again omega t. So here 1 is fired, and here I am going to have actually 5 going off. 5 will go off only where I have shown like this. So here 5 goes off, right? So that means for 30 degrees I am going to have 5, 6, 1 conducting. So for this duration I will have 5, 6 and 1 conducting, even for R load. I am talking about R load. If 5, 6 and 1 are conducting, all the 3 phases are connected to the load. So if I am trying to look at the voltage across ZA, so this is VZA. So VZA is going to be VAN itself. So whatever is VAN, so something like this, is going to be the voltage waveform. This is VAN. If you look at this portion between these two, that is where 1 is fired and it is 5 is going off. that is exactly this portion of VAN. So I'm going to have VAN coming up during this portion. But after that I'm going to have 6 and 1 conducting until 2 is fired. So 2 is fired only at this point. So until 2 is fired, I will have 6 and 1 conducting. If 6 and 1 are conducting, 6 belongs to B phase and 1 belongs to A phase. So it will be VAB by 2. Please note, if I try to look at VAB, VAB is going to be actually 30 degrees ahead of VA. So it would have almost reached peak even earlier. So it would have been coming down slightly. So I have to look at what is the difference, but this is going to be VAB by 2. I will have VAB by 2 because I'm going to have VAB coming up across these two loads simultaneously, that is ZA and ZB respectively. So I have to look at what is the voltage across ZA. So load per phase voltage. We are looking at per phase voltage of the load. So it will be VAB by 2. Then again, when I fire 2, I'm going to have until this point where I'm going to have the voltage of B goes into positive direction. 6 will continue to conduct. 6 will not go off. So I will have 6, 1, 2 conducting here. 6, 1 and 2 conducting here. If 6, 1 and 2 are conducting here, anywhere 3 devices conduct, I will have per phase voltages coming up directly. So I will have the per phase voltage which is again VAN. So I may have a jump in the voltage, something like this, and then this is coming down. So this is again VAN during this portion. So I will have VAN, VAB by 2, again VAN, then 6 will go off. So 1 and 2 will come, 1 and 2 will correspond to VAC. So VAC by 2 will come. So I am going to have line voltage, half of line voltage and phase voltage coming up alternately. But will there be any zero voltage at all? That we have to check. So if I say that 1 and 2 are conducting here, maybe I am going to have, this is VAC by 2, maybe. I don't know the magnitudes. I have to analyze it clearly. Unless I really analyze the magnitudes, it's difficult. After this, 1 and 2 have conducted. Now 1, 2, 3 will conduct. I hope you understand. When I fire 3, still for 30 degrees, I will have 1, 2 and 3. So 3 is fired here. 3 is fired at this point. So I am going to have in all probability 1, 2, 3 conducting. Right? Is 3 fired there? Have I made a mistake? Here. So have I made a mistake in writing the firing angles? This is 1, this is 2, this is 3. Sorry. This is where 3 is. This is where 3 is. So this has to be erased again. Right? So this is where 3 will be fired. 3 is fired here. So when 3 is fired, still there is some amount of positive A phase voltage left over. So 1, 2, 3 will conduct together. Right? So I am going to have actually for the first 30 degrees starting from alpha, I am going to have 5, 6, 1. Then for the next 30 degrees, I am going to have 6 and 1. Then for the subsequent 30 degrees, I am going to have 6, 1, 2. Then I will have 1, 2. Then I will have 1, 2, 3. Then I will have 2, 3. This is the sequence that it is going to go on. Right? When 2 and 3 are conducting, there is no A phase voltage. A phase will not carry any current. A phase load will not carry any current. So here there is no current through A phase. No current through A phase. So I'm going to have essentially whatever is the VZA will be 0 during this 30-degree interval. After that we will fire 4. Once we fire 4, again we will get negative side voltage, because it will essentially allow the current to flow in the opposite direction. Is this clear? We are looking at each of the conduction of the device, like what is the combination of devices that conduct for one interval. And I have taken a specific case, alpha equal to 30. When I take alpha equal to 30 with R load, this is the way it is. If it is RL load, it's more complication. I hope you understand, because if it is RL load, the inductance will forward bias the device even after the voltage goes negative. If the voltage goes negative, still I am going to have the device to be forward biased. So if the device is forward biased, I am essentially going to see that even after, for example, here we said phi will stop conducting once I have the C phase voltage start going negative, but phi will continue to conduct even after the C phase voltage goes negative, right? So which means the 3 device conduction can extend for longer and longer, depending upon how much is my inductance voltage. But if that continues until the next device is also fired, then always 3 devices will conduct. That's when you won't have any control. All the time per phase voltage is going to come up. So in which case you will hardly see any control over the output voltage. So you would see more control over the output voltage, especially in the case of RL load only if alpha is somewhat larger. Otherwise you are not going to see much of control over the output voltage at all. So much so for AC voltage controller. So in AC voltage controller we had seen only single phase and 3-phase star connected case, R load, RL load, and for single phase I said why alpha greater than phi only will give you control, where phi is the load power factor angle. We have not looked at any rigorous mathematical expressions. I just want you to understand how it works. That's it. Okay. Now the next one that we are going to take up for AC to AC converter. The second type of AC to AC converter is cycloconverter. Cycloconverters are again generally made up of SCRs, thyristors. That's the reason I'm taking up all those circuits which are involved with thyristors. I'm taking up all those circuits, and that is the reason why I wanted to just take up this also along with line commutated circuit. What I mean by line commutated is supply voltage is trying to make sure that the device that goes off is reverse biased for sufficient amount of time. You don't have to apply any external voltage. The supply voltage itself is taking care of the current transfer from one particular device to another device. So cycloconverter also falls under that category. So because of which this one heavily depends upon the supply voltage being AC. The output voltage is not going to aid in commutation. More than that, the supply voltage is going to aid in commutation. That is the way it is going to work. So this converts AC to AC directly, and if I have 50 Hertz, for example, I may be able to convert it only to a lower frequency. Hardly ever we will use it for a higher frequency conversion. So cycloconverter will convert both magnitude as well as frequency, but the frequency will be decreased or stepped down in frequency as far as input-output relationship is concerned. So normally input frequency will be higher than the output frequency. That is the way normally the cycloconverter works. So if I am trying to look at the basic principle of a cycloconverter, we'll look at the circuit a little later. If I am going to have, let us say, an AC supply single phase somewhat like this, I am going to have the single phase AC supply like this. If I use a rectifier for rectifying one cycle, so I am going to rectify this as well, and I am going to rectify this such that I am going to get basically this as the output across the load for 2 half cycles. I am talking about 2 half cycles. For rest of the 2 half cycles, I am going to have another rectifier which is connected exactly like a dual converter in the opposite sets. Then I will have this portion and this portion coming up as the output voltage across the load. So I have got 2 halves of positive half cycle, 2 halves of negative half cycle. This is going to repeat itself. Let us say I'm going to again have 2 halves of positive half cycle, and then I'm going to have 2 halves of negative half cycles. Now what will be the frequency? Forget about the waveform. Waveform is not sinusoidal. Very clear. There is no doubt. But what about the frequency? The frequency is going to be 50 by 2. Right? If this is 50 hertz, I'm going to get 50 divided by 2. I'm going to get 25 hertz. Right? I cannot do this with diodes. I hope you understand, because diodes will conduct no matter what if they are forward biased. So I can't even have a dual converter with diodes. I hope you understand. I can't connect back to back. It is going to essentially burn completely, because one will have plus on the top and minus at the bottom. The other one will have minus at the, again the other way around. So you will try to connect the 2 plus and minus. Imagine the dual converter. I am talking about a dual converter. So I am going to have something like this, single phase. So I am normally going to have it with thyristor. It cannot be made with diode, right? And I am going to have a load here, right? And this is my input supply voltage, right? On the other side, I am going to have again another fully controlled converter, somewhat like this. So if I am having diodes, I will not be able to delay the conduction at all. So for this, if this is plus and minus, for this, actually this will be plus and this will be minus if it is diode. So I'm trying to connect the plus and minus together, right, directly, and that is definitely not done. Huge current will flow. So you cannot do this. That is the reason why in the dual converter we wanted to have this as plus and this was minus. We made this alpha greater than 90, whereas this alpha less than 90. If you may recall, this is what we did in the dual converter, right? And after all, we had the input from the same AC voltage. So I would say maybe this went here and this went here. This is how they were connected. You remember, this is the way the AC supply voltage was connected. So here is my AC supply. Cycloconverter is no different from the dual converter as far as the circuit diagram is concerned. Only difference is, in dual converter, we were operating one at alpha less than 90, the other one at alpha greater than 90, and we were making sure that alpha 1 plus alpha 2 equal to 180. This was the control that we wanted to have, if you may recall. So that the average voltage across this and the average voltage across this, averages are the same, not the instantaneous values. They were different, right? So the averages were the same, because of which we actually had put a reactance here. If you may recall, we had put some reactance here. So that if there is any di by dt, that will be limited, and the reactance will also have some amount of resistance, because of which the current will be limited. Magnitude of the current will also be limited. But in this case, in cycloconverter case, If I may call this as the negative side converter, which is N converter. I may call this as positive side converter or P converter. I will make P converter work for a distinct number of half cycles. I will make the N converter work for a distinct number of half cycles. Both of them will not work simultaneously. They will not work simultaneously. And each of them functions as a rectifier in its own right. When P converter is functioning, it is working as a rectifier on its own. And N converter is quiet. It is not working because you will not give any pulses to the N converter. So N converter pulses will not be released until P converter current comes down to 0. Then you will release the pulses to N converter, holding off the pulses to the P converter. So what is going to happen is, for the first two half cycles, for example, I will have the current flowing like this. Right? So this is during P converter operation. So this is first two half cycles. The next two half cycles, I will have a current flowing like this. This is for next two half cycles. Right? So I am going to have, for the first two half cycles, the current is going with plus here and minus here. For the next two half cycles, the current is going with plus here and minus here. Right? So which means in both the cases, I will have alpha less than 90 only. Both alpha 1 and alpha 2. So this is for cycloconverter operation. Both alphas will be less than 90, but they will work completely disjointly. They will not work together. When one is working, the other one will not be working, and vice versa. Whereas, when I am talking about dual converter, these two work together. One works as a rectifier, the other one works as an inverter, and they work together such that I am going to have the DC link voltage average value to be the same. So here this is for dual converter. Right? So what I can do is to have basically multiple number of half cycles being worked with P converter. Make sure that the current goes down to 0. So if I have RL load, I have to continuously sense the current. If I don't sense the current, I can get into trouble. Because I will still have maybe some positive negative left over, and if I try to fire this, there will be a dead short because this would not have gone off. And this will start conducting. So I can have really a dead short circuit between the two converters, P converter and N converter. So I have to make sure that the current really goes down to 0 in the P converter and the load. And after that I should start the other half cycle of the output. So we are looking at two input as well as output. Both are AC. So I have to talk about whether it is a positive half cycle of the input, positive half cycle of the output, negative half cycle of the input, or negative half cycle of the output. So if I want positive half cycle of the output, I have to make use of P converter. If I want the negative half cycle of the output, I have to make use of the N converter. So distinctly I have two converters which are connected back to back, which are going to work in such a way that one is disjoint with the other. They are mutually exclusive. They are not going to work together. But I have to make sure that the current comes down to 0 before I release the pulses for the next set of devices. Right? And when I release the pulses to the devices, just like what we did, 1 and 4 will be given pulses during positive half cycle of the input. And 2 and 3 will be given pulses during the negative half cycle of the input. And I may call this as P1 because P converter, P2, P3, and P4. So P1 and P4 will be given pulses during the positive half cycle of the input, provided I want positive half cycle in the output as well. Right? Whereas if I want the other way round, if I want the negative half cycle at the output, then I have to take care of these devices. So if I may call this as, this is coming to A. So if I say that this is coming to this one, so I should call this as N1. So this will be N4 and this will be N2, this will be N3. So I should correspondingly make sure that N1, N2, N1, N4 will be given pulses if I want negative half cycle in the output, but prevailing thing is the positive half cycle as far as the input is concerned. So I have to look at the input as well as output simultaneously. So this is going to be the way your complete converter works. So this is single phase to single phase operation. I can have the same thing for single phase to three phase to three phase to single phase. So I can have multiple types of cycloconverter connections. So when I am talking about the single phase to single phase, that too full wave, because I'm not leaving out the other half. I'm always using both the halves of the input wave, whether it is positive half or negative half. I'm making sure that I'm making use of both of them. So it is a full wave controlled converter. What I have used is a full wave, fully controlled converter. So when I use a fully controlled converter, even single phase to single phase conversion will require 4 plus 4, at least 8 devices. You get my point? So if I want single phase to single phase full wave cycloconverter, I will require 4 plus 4, 8 devices minimum. I will require at least 8 devices. Only then I will be able to do full wave to full wave. If I want now 1/3 of the frequency, I can make 3 half cycles positive, 3 half cycles negative. So you guys know how to reduce the frequency further. But we will not be able to increase the frequency with single phase, because the thyristors will go off only when it is starting to go into the negative half cycle. So I cannot increase the frequency unless I use some kind of forced commutation. But the moment you use forced commutation, the entire thing will become very, very complex. So generally, we do not use SCR based cycloconverter for increasing the frequency, because if you want to increase the frequency, you necessarily need to put forced commutation circuits. You have to turn off the devices somewhere in between. Let us try to take a look at a 3-phase half wave to single phase cycloconverter. I am going to use a 3-phase half wave rectifier, which is hardly ever used. Just for continuity's sake, I am slowly going with, slowly increasing the complexity. So, if I am going to have 3-phase input like this, you guys remember the half wave rectifier for 3-phase. We said that for every phase, we have to have 1 thyristor. Right? And then if I connect the load will be connected between this and the neutral. This is the way it is connected. Right? This is a half wave rectifier. We have not included the N converter because this is a P converter. If I may call this as the P converter, I should call this as P1, this is P2, and this is P3. And this is VAN, this is VBN, and this is VCN, with this being the neutral. Obviously, I have to have one more converter with opposite connection of the SCR. So, I can imagine that from all these 3 terminals, because I am using the same source, I am not going to use a new source. The same source is being used. But I am going to have essentially 3 thyristors connected in the opposite sense. So this is the second one and this is the third one. 3 thyristors are connected in the opposite sense and these are star connected now, and I can connect this to the same point here. You get my point? So if I try to fire P1, P2, P3, I am going to have this as positive. So this is P positive and P negative. Whereas if I try to fire, let me say this is N3, this is N2 and this is N1. So if I try to fire N1, N2, N3, I am rather going to have this as negative. So I should say this is N negative and this is N positive, because it is exactly connected in the opposite sense. But in this case, we will get only half wave conversion. So if I am trying to draw all the 3-phase voltages, for example, so let us say this is, okay, I have to at least draw a couple of cycles, but for which I have not kept space. But I am going to have something like this. So this is the second phase. And this is the third phase. Right? So I have to wait until my other phase, actually that is the P converter current becomes 0. That's what I told you. So if I am actually firing the P converter, I am starting off from here, I may get all these voltage corresponding to P converter. Maybe I will do it until here. So I have given firing pulses only to P1 and P2. And I am not giving the firing pulse to P3. I will wait until the current comes down to 0. Now I can try to give the firing pulse to the next converter, which is the N converter. I am just showing as though I have got only 2 overlapping half cycles. So I have given this correspond to P1 and this is corresponding to P2. And I have not even given for P3, but I will give for again this corresponds to probably N2, then I will give it to N3 and so on. So I will have again reduction in the frequency, but I have taken as though alpha equal to 0 or even less than that. So I am starting right from the transient condition. Otherwise alpha should be calculated somewhat like this. That's what we said. So we are looking at the whole thing as though we have to fire the P converter such that ultimately the current will come down to 0. If you keep on giving firing pulses, the current will never come down to 0. So you will not be able to go to negative half cycle at all. So once you hold off the firing pulses to the P converter, you should wait until the current comes down to 0. So it's very important in a cycloconverter to sense the current. Without current sensing, you cannot release the firing pulses to the other set of converter. Otherwise, you will have a dead short circuit. You will have a big problem with the, the connection of the 2 converters, because you are trying to connect completely opposite polarity together. That's the reason. So this is typically a 3-phase to single-phase cycloconverter, where I have 3-phase supply in the input, whereas the output is single phase. And it is not sinusoidal. It is still not sinusoidal. Right? Now if I want 3-phase to 3-phase, for example, or let's say first of all single-phase to 3-phase cycloconverter. How do we really connect single-phase to 3-phase? I have 3 different loads, clearly. Right? R phase, Y phase and B phase, because at the output I am going to have 3 phase. But what I have in the input side is single phase. So I have to have for each of the phases 1 P converter and 1 N converter. Each of the phases should have independently one P converter and one N converter. So if I have 3 phases, I will have 3 P converters, 3 N converters. So I will have 8 multiplied by 3, which will be 24 devices. Cycloconverter uses really large number of devices. So let us try to draw for single phase to 3 phase. Right? So I am going to have this as my power supply, which is common for all the converters. So I am essentially going to show it in the form of, let us say, simply let me show it like this. This is the P converter. Okay? And let me show the other one either here or I can show it here as well. So I am going to have the other one as the N converter. Right? I had to show similarly 2 more things. So this is A phase or red phase. Then I am going to have one more yellow phase, or let me say this. So I am going to have one more set of P converter and N converter. And I will have one more set of P converter and N converter. So I have got each of them having 4 devices. There are 6 such things, so 24 devices. Now I will connect this first of all to this. Now the output is connected to a load. Right? And normally I am going to have plus here and minus here if it is working as a rectifier. The same thing when this is working as a rectifier, I am going to have plus here and minus here. But this plus has to be connected here and this minus has to be connected here. The other way around, like a dual converter. Right? So I have connected just the opposite polarity. So this is A phase load. Okay? And this is P converter A phase. This is N converter A phase. Okay? Now from here I am going to connect this to this. From here I am going to connect this to this. Same single phase supply goes everywhere. I am not having any more supplies. I have only one single phase supply. It is going here. Okay? So if I may call this as 1 and 2, these are the input sides of the other, I can say line and neutral otherwise. This is line and this is neutral. So between line and neutral, all the converters are connected. Now I am going to have similarly, this is P converter B phase and this is N converter B phase. And this is going to be P converter C phase. And this is going to be N converter C phase. Okay? Now the input is very simple. I am going to connect it the same way. So from here again I will take it up. I will connect it here. And from here I will take it up. I will connect it here. From here I will connect it. So all of them are connected to the same input. The input is essentially the same. So I have to again show from here, from the same point, I can connect it to this and I can connect it. So I have to take it here. So I have taken it here. So the same thing I can connect it here. All the inputs I have to connect. But when I give the firing pulses, I have to make sure that I give the firing pulses always to 1 and 4 together and 2 and 3 together as far as every converter is concerned. And if 1 and 4 are conducting during positive half cycle, I better connect them in such a way that they will conduct during positive half cycle of the input supply voltage. These things I have to take care. So when you make a cycloconverter circuit diagram, if at all you do that in PSIM, there is a demo available also for cycloconverter. You should see how it is connected together. So this is how it is connected. Now I have to again connect a load. So maybe I just take a load like this. This is connected here, this is connected here, this is B phase load. Right? So this is ZB. Let me show this as ZB, that is B phase load. This is positive and this is negative for this converter. And as far as this is concerned, here is going to be positive and this is going to be negative. So this positive should be connected to negative and vice versa. The other way round. Right? Same thing is true for this particular case. Again, I am going to have here this as ZC. Right? So I will have this as positive and this as negative. Here I am going to have this as positive and this as negative. So this positive will be connected here and this negative will be connected here. So that the current flows in the opposite direction. When it is rectifying, P converter is rectifying, I will have the current in this direction. When N converter is rectifying, I have the current in the opposite direction. That's all that it is facilitating. Right? You are going to exactly have dual converter kind of connection. So, if I have made a connection like this, how will I make sure really that I am going to have, the A, B and C phase supplies 120 degrees away from each other. They have to be 120 degrees away. So normally when I try to do single phase to three phase, I would like to have 3 half cycles or 6 half cycles or 9 half cycles. So that if I have 3 half cycles of, the input coming up at the A phase, then from the second half cycle or third half cycle onwards, my B phase can start. You get my point. If I am going to have my A phase output somewhat like this, and then it is going to have 3 half cycles like this. This is A phase, ZA voltage, VZA. VZB can be from this half cycle it can start. You get my point, because this entire thing corresponds to 180 degrees. What I want is 120 degree shift. So 2 half cycles will correspond to 120 degree shift as far as the output is concerned. You get my point? So I would have essentially these 2, 3 coming up as the half cycle here, and these 2 will come like this and so on. So this will be VZB. VZC obviously has to start from here. Right? They have to essentially be shifted by 120 degrees of the output wave. Output wave. You get my point? So I am going to have essentially these going as positive half cycle. So I will have essentially negative half cycle coming up like this here. 3 half cycles like that. Right? So this will ensure that I get exactly 120 degree phase shift between A phase, B phase and C phase respectively. So far whatever we have talked about, we are not having any voltage control. Ideally what I would like to have as the waveform is somewhat like this. It should be sinusoidal. This is what I would like to have. And in the other side also I should have sinusoidal voltage like this. Ideally this is what I would have liked to have. Right? Because most of my loads will accept only sinusoidal output voltage. They will not accept non-sinusoidal output voltages. What I am getting is definitely non-sinusoidal. I hope you understand. Because 3 Vm by pi, whatever we are getting, 3 Vm by pi cos alpha, that is the value I am getting if I am firing it at a particular alpha continuously. So it is as good as having a square wave voltage. On an average basis, if I try to look at it, it will look as though if I look at the average value, I will have a square wave like this and then I will have a square wave like this. This value may correspond to 3 Vm by pi cos alpha. This is how it is. It is somewhat like this. And definitely I do not want that, especially if I am trying to apply this to a synchronous motor drive or induction motor drive. Cycloconverters are generally used with synchronous motor drives in a big way, because synchronous motor drives normally are of megawatt level rating, very, very large capacity most of the times. And synchronous motor drives generally, because they are of large rating, they will also have a huge inertia, very large inertia. If they have a large inertia, it is going to take a while for them to vary their speed. J d omega by dt equal to Te minus TL. That is the equation F equal to ma. Something similar to that. That's what I'm talking about. So you are going to see that it takes a while before the speed changes even a little bit. So the response time is really, really large for a synchronous motor drive, which corresponds to megawatt level rating. SCR is also slow, and they can handle very large power. So they all match very nicely. Thyristor based any converter will work slowly. They are much slower than IGBT or MOSFET or any of them. And they can handle single-handedly almost 30 megawatts of power without any difficulty. Because of which, for high power drives, we generally tend to prefer thyristors. And cycloconverters reduce the frequency. Most of the times, synchronous machines may be run at slow speeds. For some kind of, cement mill where you are trying to grind, limestone and so on and so forth, all those things work very slowly. It is inching. Most of the motor drives will be inching slowly. So in those cases, these can come in handy. From 50 hertz, you may come down to 10 hertz or 5 hertz. So in those cases, cycloconverters come in handy. So motor drives will not accept generally anything other than sinusoid. So how am I going to really get a sinusoid? That's what we'll have to think about. So if, let us say, my output wave is having maybe 5 or 6 half cycles like this. In fact, if I am going to say 50 hertz to 10 hertz, I will have 5 half cycles in the positive and 5 half cycles in the negative. If I am coming down to 5 hertz, I will have 10 half cycles in the positive, 10 half cycles in the negative. So I may have something like this continuously coming up, right? So this is the way it is going to be. I can approximate this to a sinusoid, provided my average voltage is really small here, somewhat larger here, somewhat further larger here, then again it comes down here, comes down further here. I can do that. I can always control my firing angle in such a way that first half cycle I have it close to 90 degrees so that the voltage is very, very small. The next half cycle I can make it 60. The next half cycle I can make it 30 or even less. Then the next half cycle I can again make it, 60. Then the next half cycle I can make it, close to 90. So this will essentially approximate my output voltage to something like this. It is starting from very minimal value. It is reaching a peak here and then it is coming down to small value. So the control for cycloconverter is not very simple because it is a continuously varying firing angle. I will be definitely varying the firing angle, but if it is an RL load, like a synchronous motor, I will have to take into account definitely there will be some negative portion of the voltage coming up. That's the reason I told you that for 90 degrees, output is 0. Only if it is continuous conduction. So I need to know what kind of load I am connecting to, and accordingly I have to calculate what is the kind of firing angle I have to give such that my output voltage approximates to a sinusoid. So it is the same thing I will be doing in the negative half cycle as well. So I may get only small voltage, this is a little larger, this is much larger, and then I'm going to get, smaller and smaller voltages. Get my point? So this is also going to approximate this entire thing to, a sinusoid somewhat like this. So I can control the output voltage approximately to a sinusoid. It is not a perfect sinusoid. It is only an approximation to a sinusoid. So I am calculating the area under the curve, which is actually 3 Vm by pi cos alpha normally, and then correspondingly I am trying to look at not 3 Vm, 2 Vm by pi for single phase. We are talking still about single phase. So I have to calculate for that and then make sure that the firing angle is adjusted accordingly. That will make sure that what I apply as the voltage is somewhat sinusoidal. And the same thing has to be replicated for B phase, shifted by 120 degrees. And the same thing has to be again duplicated for C phase, again shifted another 120 degrees. So this control is definitely not simple, but especially when there were no other devices other than thyristors. That was in 1970s. This was really leading, it was ruling the rooster for as far as the synchronous motor drive control was concerned. Even now, many of those drives are there in many of the power stations which are working quite well. NTPC power stations, many of them use cycloconverter fed synchronous motor drive for many of the controls, and they are still working well, so nobody has tried to retire them. They are still working very much fine. That's not a problem. Now actually with the advent of wind energy conversion system, these things are coming back somewhat, because as far as wind energy conversion system is concerned, we will have a variable frequency of output from any of the AC generator. If I have an AC generator, it will be rotated by a wind turbine, and the wind turbine is definitely going to have a variable velocity. It's not going to have a constant velocity. If it has a variable velocity, the output what I am getting from my, the generator, that is going to be at a different frequency. If I want to feed it to the grid, I have to ultimately convert that into 50 Hertz. If I have to do that, normally what we do as of today is to first of all rectify the AC voltage into DC, and the DC is again converted back into AC with the inverter. So you have two stages of conversion, because of which there are many losses and huge amount of complex control. I'm not saying cycloconverter is a simple control, but this is one stage of conversion. Directly you are converting from AC to AC. But the question is whether we can convert from a variable frequency always back to 50 Hertz. So for that there are several control methodologies that have evolved. So cycloconverter is again having a rebirth. Although it had become obsolete, now people are looking at it with a renewed vigor, because it can be used basically for the control of wind energy conversion system from variable frequency output to a constant 50 Hertz output, which can be fed to the grid, right? So much so for the voltage control. I am not getting into great details of cycloconverter, because this is really not taught by many of the power electronics teachers. But I thought because it is reviving, at least you should know what is a cycloconverter. That's the reason. Okay. Let us try to take a look at 3-phase to 3-phase cycloconverter. If I want 3-phase half wave to 3-phase ultimately the output cycloconverter, half wave requires 3 devices. 3-phase half wave requires 3 devices. P converter will require 3 devices. N converter will require 3 devices. So 6 devices per phase. And I want 3 phases at the output. Right? So which means 18 devices minimum I'll require if I want 3-phase half wave. If I talk about half wave, right, I will require every phase will have one P converter and one N converter. And P converter will require 3 devices, N converter will require another 3 devices. So I will require 6 devices per phase. So I will require 18 devices if I am talking about half wave. If I talk about full wave, I have to double it. I will require 36. So we will require 36 thyristor devices or SCR devices and their control independently if I want to do it from 3-phase to 3-phase. Right? So if I am talking about half wave, basically the circuit will be somewhat like this. So these are the 3 phases and I am going to have 1, 2 and 3. So I should say P1, P2, P3 corresponding to A phase. Right? And I will also have the neutral, of course, and from here I have to connect it to, so this is ZA. Right? So I have to show N converter again. So I may show something like this. Right? So these are the 3 terminals and I am going to connect this here and I can call this as N1, N2, N3 for A phase. Right? So this has to be connected here. So I have to connect this. Right? And then connect it here. Right. Now this has to be connected the other way around. Right? Okay. So this has to be connected here. And this has to be connected here. Second phase. And this has to be connected here. Third phase. That's it. So it is just the other way around. Right? Neutral is already connected. So I don't have to do anything with respect to neutral. Now from the same 3 terminals I have to do this for B phase. Then I have to do this for C phase. So I have to have 3 more devices, for example, connected from here. So 1 phase, 2nd phase and 3rd phase. So all 3, again I have to have one like this and then I can have from the same 3 terminals, I can connect it the other way around. Right? So this will be B P1, B P2, B P3. This will be C, B N1, B N2 and B N3. Right? Okay? Now these 3 are connected together and I am going to have a load which will be ZB and that will be connected with the neutral. This is neutral, same neutral, so I can connect it here. Right? This is the neutral. So I have connected it here. So the same thing has to be done with respect to this as well. So these 3 terminals are coming here. These are connected together. Now this has to be connected here. Neutral is anyway connected already. So it doesn't matter. Similarly, I'll have to do it for C phase. Right? You are taking the same 3-phase supply, 3 devices in forward direction, 3 devices in reverse direction. Half wave. Right? So I want you guys to draw the full wave. I am sure you can do it. It will take some time. or you use just the positive connected symbol and negative connected symbol, doesn't matter, right? I'm sure you can do that. It should not be a problem. So this will require totally 18 devices for half wave, 3-phase to 3-phase, whereas 36 devices for full wave, right? So AC to AC converter, basically we have discussed only two types. There is one more thing called matrix converter, which I am not getting into. We'll see if time permits towards the end. I will look at matrix converter. Otherwise, I don't want to get into matrix converter. There is one more converter which is AC to AC conversion is possible. That is matrix converter. Matrix converter I am not looking into right now. Okay. So we have seen only single phase and 3-phase AC voltage controllers where frequency will be a constant and magnitudes could be changed. RMS value of magnitudes could be changed. But the major problem is non-sinusoidal output. And the other one what we have seen is cycloconverter, which can convert single phase to 3-phase or single phase to single phase, 3-phase to a single phase or 3-phase to 3-phase. All of them can be done, but frequency generally is reduced and sinusoidal output approximation can be done. It will be very difficult to obtain exact sinusoidal voltage. So the next topic that we are going to start off is on DC to DC converter. I'll just tell you what we are going to cover. Today I'll just leave it at that. We'll really venture into DC to DC converter in the next class. Okay? So DC to DC converter is something similar to what we had seen as AC voltage controller. So we are going to probably chop off some portion of the voltage. We'll not apply the voltage for some time. We'll apply the voltage for some portion of the time. So if I take, a switching action which has a period of 10 kilohertz. High frequency, really high frequency. So normally DC to DC converters work on high frequency in terms of kilohertz at least. It can be of the order of megahertz if I'm talking about very, very small power levels. If I'm talking about motor drives, then it may be of the order of a few kilohertz, right? So if I am having a DC supply like this is the input, right? With respect to time. I'm not writing omega t because it is DC. With respect to time, it is a DC. This is the input. If let us say this is 100 volts, but what I want as the output is 50 volts. If I apply 100 volts for 50% of the period and rest of the 50% I don't apply any voltage. So I am essentially looking at a voltage somewhat like this. Maybe I'm going to apply it for 50% of the time. I don't apply it for the rest of the 50%. Again I apply it for 50% of time. I don't apply it for 50%. Like this. I repeatedly do this. So I'm doing on-off control, basically, nothing else. So when I do on-off control like this, and if I do it pretty fast, right? So if I am applying it, for example, to a DC motor, it may not realize it is not getting any voltage. The current will start coming down, but because of the inductance that is present in the DC motor, and I may add some inductance in my circuit, the current will increase, decrease, but the ripple may be limited, which will indirectly, give me 50% of the voltage only as the output. Because I am going to get whatever is V in multiplied by T on plus 0 multiplied by T off divided by T on plus T off. This is going to be the average voltage. This is going to be V0. So V0 average will be somewhat like this. So how long I keep the switch on as compared to T on plus T off? T on plus T off happens to be the period of this particular chopping action. Okay. So this is essentially the typical working of a DC to DC converter. So obviously I cannot use a transformer to step down or step up DC voltages. It's only meant for AC voltages. So I can use this kind of a power converter with a switch which can turn on and turn off at very high frequency rate, because of which I will be able to get a variable output DC value. So DC to DC conversion is very commonly used in certain applications. One of them is SMPS, switched mode power supply, which we use in many of the personal computers. All the personal computers, normally PCs, use SMPS, switched mode power supply. So there what I get may be very high value of DC. From that I may try to get 5 volts, 15 volts, plus 12, minus 12. Right? Whatever my CD-ROM drive requires, whatever my other, ICs require. All those things may be obtainable using DC to DC. Another one is battery-driven vehicle control. You guys might have seen in many of the airports and all, for cleaning or for going from one terminal to another terminal, there will be a vehicle going which will be pretty quiet because it is having an electric motor. It doesn't have any IC engine because pollution has to be avoided there. So normally what it has is a battery inside, and the speed control is done using a DC to DC converter. Stopping, starting, acceleration, retardation, whatever you want to have, all those controls can be implemented very easily with the help of a DC to DC converter. So battery driven vehicles. And some of the battery charging circuits, those also use DC to DC converter. For example, I may have a solar PV from which I want to charge a battery. So in which case solar PV may not give the voltage what is required by the battery. So I might have to use some kind of DC to DC converter to adjust the voltage level of the solar PV output to match with what is the battery output, battery's input voltage. So because solar PV will not have a constant value of output voltage all the time. It depends upon the temperature at which it is operating and also on the illumination level. Illumination level normally decides how much is the current that is coming out, and the temperature indirectly decides what is the kind of voltage, and what kind of load I have connected, that also decides the voltage. So you are not going to have a constant voltage. So if I want to connect a solar PV to a battery, generally it is not done directly, it is done through a DC to DC converter. So I can say battery charging application using solar PV. If I want to charge a battery using solar PV, in these cases also DC to DC converters are used. So what I have shown you is to reduce the voltage, because I cannot increase the voltage using this kind of a configuration. There are configurations which may have, the capability to increase the output. The power cannot increase. Obviously, whatever I give as the input power will be equal to the output power, assuming that the DC-DC converter is lossless. So I can have, so this kind of converter is known as buck converter, where I am going to step down the voltage. The second type of converter which we will be studying will be boost converter, which will be step up converter, which will do step up operation. Here normally we will have an inductor inside which we will try to store some energy, then we will try to release it whenever it is required. So it is like creating a make-believe kind of situation where the inductance stored energy plus the voltage together will look as though the output voltage is increased. So step-up converter invariably uses a large inductance to store the energy for some time and then release it whenever I want a higher voltage at the output. So this is the second type of converter we will be looking at. The third type of converter we will be looking at will be buck boost converter, which can either reduce or it can increase the voltage. So buck boost is another third type of converter which may be used typically again in a solar PV application, because I may have a range of voltage in solar PV, let us say from 36 to 48, but my battery voltage may be only 42. So I may have to step up the voltage or step down the voltage. So whenever I have a variation, huge amount of variation in the voltage, whereas the output voltage I require is somewhere in the middle, I would like to use a buck boost converter. And all these three converters, what we will be looking at, are not going to have any isolation between input and output. So these are basic DC to DC converters without any isolation between input and output. Isolation normally is always obtained with the help of a transformer. So when I don't have a transformer, these are generally known as non-isolated DC-DC converter. These three are known as non-isolated DC to DC converter. Whereas we will also be looking at a few isolated DC to DC converter. As we proceed, I will tell you what are all the isolated DC-DC converters that we will be looking at. So we will start off in the next class with buck DC to DC converter or step down DC to DC converter. Right? For this portion, specifically I will be referring to Daniel Hart's book. Daniel Hart has given this portion extremely nicely. So I will try to refer to that book specifically for DC to DC converters alone.